So I wanted to record a quick video showing you how to compute the EDTA titration curves with Hydra and Medusa, because this is a really powerful, simple program. So I'll do that by sort of computing the example that we just did by hand in the previous video, 12.3. So what I have written on the whiteboard behind it are just the constraints of the problem. So we had a 50 milliliter volume of calcium 2 plus at 0.04 molar, and our titrant was EDTA at 0.08 molar. And remember, this was buffered to a pH of 10.0. We computed the equivalence volume in this system to be 25 mils, and then what I have is a table of the summary of the 3 points that we computed at the different volume additions. So V add is the different volumes of the titrant EDTA that we added, and then the resulting computed P calcium, so the negative log of calcium in that case. So we started at 0.1, which was 5 mils, and that gave us a concentration of a P calcium of 1.54, and then I just converted that to log calcium, which the only difference between P and log is just the negative, because P is negative log, so you just get an inversion, because that's what our Hydra Medusa is going to compute. And then we did 25 mils, which is coincident with our equivalence volume, so that's the equivalence point of the system. That gives us a P calcium of 5.85, and then the last addition is 1 mil past equivalence, or 26 mils. That gave us a value of 8.72. So how do we set this up? So open up Hydra, our database, and we just need to select the relevant components here. So of course this is in water, so I'll leave the default proton here, but then I need to grab EDTA and calcium. So EDTA is a weak acid, so I go to carbon and then I grab the EDTA, and the form that comes default is the Y4 minus, which is what we want. So I'll select that, and then I'll go to calcium, and we need the calcium 2 plus, which is the only species we have available to us. So that's it. So I'm going to go to file, and I'm going to, oops, not that, file, save and exit, and then save file and make a diagram of Medusa. So I just ran this before this, so I have a name EDTA-calcium. So I'll just overwrite this and click yes. And now we're presented with Medusa. So everything is in the form that we need it to be in, actually. So we don't need to do any exchanges of components. So I'll click run and then make a diagram. And then this is where we need to input the relative parameters, or relevant parameters, I should say. So we want, on our y-axis, we want log concentration. Ideally, we do negative log concentration, but that's not an option because that would be the p-value here. So we'll deal with log, but that's what we're going to be computing then, are the log calcium. And then we're probably going to want to run this up to, say, minus 12-ish. You may have to experiment with this, but actually we could probably get away. Let's just run this up to minus 10, because it looks like our largest value here is 8.72. So maybe I'll run this 11 just to make sure we get the complete sort of symmetric curve. And then on the x-axis, we would want technically the volume of EDTA that's added, but we don't have that as an option. But what we can select is the total concentration that's varied in the system, and we'll vary that concentration up to from 0 up to its formal concentration. And so our formal concentration was 0.08. So what that means is it's essentially doing this as an arbitrary volume of the system. That's why concentration is on the x instead of volume, because there's no place to input an initial volume of the system, so it can't compute a volume added. Instead, it just computes what the concentrations of everything would be with an equivalent concentration of EDTA added to the system. But I'll show you how to convert that to volume just using an M1V1, so it's very straightforward. So I'm going to set this from 0 up to the formal concentration. That'll encompass our entire range. And then for total concentration of protons, we're buffered at pH 10. The default is 1. This is in molar. So remember, pH 10 would be 10 to the minus 10. So 10, or it'd be 1 times 10 to the minus 10. So 1e minus 10 would be the concentration of our proton solution, buffered in this case. So I'll select that as OK. And then the calcium concentration, our formal concentration, was 0.04 molar. So I'll type in 0.040 and click OK. And so this is everything we need for this system. So I'll go ahead and click Make a Diagram. And that's going to compute a diagram that looks like this. And oh no, it doesn't quite encapsulate all of my calcium. Um, let's see. So I actually went back here to the select diagram and I just changed my axis down here to -14 to catch all of that. So from 1 to -14. I also forgot to mention that we'll want to compute this at an ionic strength of 0.1. So remember, the ionic strength impacts the concentrations in terms of their activities. So the reason I'm putting it at 0.1 is because you'll notice in your textbook all of the conditional Kf values, the formation constants for EDTA complexes, are computed with mu equal to 0.1 because that's a more realistic solution. So if we want our numbers to be closer to the computed numbers or vice versa, I want to do this at 0.1. Of course, if you have a system where you know the ionic strength to be something different, you can input that here and that'll adjust the activities in the systematic treatment. So I think everything else should be the same and look good. So I'm going to click Make Diagram. It's going to compute that. Yep, and that looks good. Okay, so what we're looking at here is log concentration of calcium on our y-axis instead of negative log concentration. So our titration curve looks inverted just simply because the y-axis, the scale, is negative instead of positive, as a function of the total concentration of EDTA in this system, which is the apparent concentration of this stuff that's being added. And so what you see here is a bunch of different lines, but the only one that's relevant to the titration curve explicitly in what we computed is this gold line, which is the calcium concentration, the free unbound calcium concentration. And you can see log concentration means that this is at high concentration to start with, and it goes through this asymptote here, this inflection, and then it decreases down here. And this is exactly what we computed or predicted from our titration curve, because here in this region, pre-equivalence, we have excess calcium. At equivalence, where the inflection occurs, we have an equal amount of both, and then as this progresses, we have an excess amount of EDTA in the system. So the scale on the x-axis is total EDTA concentration in millimolar, which is different than what we had in a normal titration curve, which is volume. And as I mentioned, that's because the system doesn't know what the volume of the solution is. And so this is an arbitrary curve that could be applied to any volume, but we would need to convert this to our corresponding volumes in order to compare our computed values to by our computed values, meaning in the previous video, to those computed by Hydra and Medusa. So let me show you how you go about doing that. So the conversion is pretty straightforward and makes intuitive sense. So it's really just an M1V1 conversion, given the known concentrations and volumes and things that we have in the system. So the M1V1 is really the concentration of the EDTA in the solution at the time, the apparent concentration, which is the thing on the x-axis. So that's the thing we're trying to compute or equate. V is our initial solution volume, which would be the 50 mils. The M EDTA initial would be the titrant concentration, so 0.08 molar, and the V EDTA added would be the equivalent of how much of that stuff that we added to the solution at that point. So, for instance, if we wanted to compute what the concentration or the apparent concentration of EDTA would be on that x-axis on the curve at 5 mils, then what we would have is our M EDTA, which is our unknown, that's the thing we're trying to solve for, multiplied by the initial solution volume, which would be 50.0 mils, equal to the original concentration of EDTA, which is 0.0800 molar. I'll just truncate that so we have room here. Multiplied by the original, or the volume of the EDTA added. In this case, that's 5.00 mils. So we can solve this for the concentration of EDTA, the parent concentration, at that volume that's added. So what that looks like is, if we solve this for the concentration of EDTA, the concentration EDTA is equal to 0.008. That's in molar, which is the same as 8 millimolar. So I have a new column here, concentration of EDTA in millimolar, just because that's what our axis is in, which is 8. So the values then we're comparing are at 8 millimolar. And know that what this means is this is the apparent concentration of EDTA that's been added to solution. It doesn't mean that's the actual concentration. That's the total concentration of EDTA. Of course, it's being complexed and speciated out, but what it really means is 5 milliliters of the original 0.08 in 50 mils is equivalent to 8 millimolar at that time. So it's essentially a dilution. That's what the curve is telling us. So at 8 millimolar, we should have then a calcium concentration, or log calcium concentration, of minus 1.54. That's what we computed by hand in the previous video. And if we look up at our curve here, let's see, I'll just open this up a little bit. We can see that at 8 millimolar, so here this line is 10 millimolar if this is 20. So just below this line, if we go all the way up here, this line here is minus 2.5, so that fits pretty well with the fact that this should be roughly exactly what we calculated. So we could go through there and then compute those for the other addition volume. So just using the same M1V1, but exchanging the volume of EDTA added here from 5 to 25 at equivalence and 26 at millipast equivalence. What I get are apparent total EDTA concentrations in the system of 40 and 42 millimolar. So I can pull up my log plot here, and what we see is that 40 coincides exactly with where we would expect the equivalence to be. That's where the inflection is. And then the value that we get for log calcium is minus 5.85, which seems to jive pretty well with our curve here. Of course, if you were going to compute this, you would zoom in and you would extract values to several significant figures off of a plot like this. And then at 40, in this case 42, we should be at roughly minus 8.72. And it's difficult to see here, but 42 would be roughly here, and we'd be just about there in the 8 or 9 range. So anyway, the goal here is not to tell you that we get exact numbers, even though they are. The goal here is to show you how you would compute these curves, because as you get more complex systems, this is a really powerful and fast tool. Once you've done it a few times, it allows you to check your answers pretty quick, especially if you're doing if you have a real-world system and you're doing an experiment with EDTA or any complexing agent. It gives you a sense for what you really have in the system. Within a matter of like 30 seconds, I compute all of the concentrations of all of the species as a function of EDTA, which is super valuable.